Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we have Kailash Patil, who is at the end of his PhD studies in Johns Hopkins University in Baltimore. And he's going to talk about auditory object recognition. Without further ado, Kailash, you have the floor.
Do I need to be standing here? Or?
No, you can walk around.
Okay.
You can walk, you have a wireless mic.
Okay. Thank you all for coming today. Today I'll be talking about auditory object recognition. So this is a brief outline of what I'll be going through. I'll give you a brief idea of what auditory objects are, what are the different kind of representations for these auditory objects. Finally, after that I'll talk about some statistical analysis where I did experiments to evaluate these auditory object representations. And I would also like to talk about the concept of attention in terms of auditory objects. So what are auditory objects? Auditory objects are, in the Oxford English Dictionary, they're defined as, object in general is defined as something that can be placed before or presented to the eyes or senses. So you can see from this that the definition or the identity of an object is interlinked between the perception of the object. So there is no unique identity of an object by itself. It has to be, it is intertwined with the perception of that object as well. So you can see why there could be difficulty representing different auditory objects. Moreover, these objects, for example, consider this image. So objects can go from, let's say, for example, one particular instrument here, or you can consider this whole section of violins, or you can consider the whole image as an auditory object, a visual object. So this leads to difficulties in representing different objects. Also, there's another added layer of variability where, let's say, for visual objects, you can have different orientations for the objects, you can have different manufacturers for these instruments, you can have different lighting conditions, and so on. So similarly, for auditory objects, you can consider like two different instruments can produce different sounds, whereas the same instrument can produce different kind of sounds depending on the playing style. For example, a vibrato versus a plain mode of playing. So there can be a lot of variations in auditory objects as well. So the main difficulty comes from this temporal aspect of auditory objects. So consider this scene where there are three different acoustic objects playing at the same time. But what happens here is all the three objects get overlapped, and that's what enters your ear. So the temporal overlap of these objects can be a difficult thing, but we are able to easily perceive the different instruments present or different objects of this acoustic scene. So I would now like to move on to the kind of auditory object representations. I will give you a brief overview of what is there and what we are proposing here. You can think of one simple way of representing auditory objects is just the waveform itself. So that's the topmost row here. People have tried to extract different features from the waveform. They've used features from like zero crossing or energy, amplitude, and so on. Another way of representing these objects is the spectrum level, which is basically the energy present at different frequencies for that object. And again, people have used different features at this level, like spectral flux or a spectral slope, and so on. Finally, as a hybrid between these two, that's the bottom representation here, which is a time frequency representation. And this is the most standard technique used for a majority of the auditory object analysis, where people generally consider a window of or a time slice of the spectrogram and then derive different features for each time slice, and this window is then shifted over time. So you get different representations which are like MSCCs and LPCCs. But what you can notice is that these don't capture all the variations and nuances in the spectrogram, and they just capture whatever occurs in that small time window. So these may not be extremely effective at capturing the characteristics of an auditory object. Also, neurophysiological studies have shown that in the auditory cortex, neurons are sensitive to various kinds of features. They can be not only just frequency and time, but they can be sensitive to different kind of patterns in this spectrogram. And you can have a sensitivity to pitch, you can have sensitivity to harmonicity, and so on. So this suggests that we should look at something which just looks more than just a short time window. In the auditory pathway, there are millions of connections happening, and these are we call the processes just below the auditory cortex. All the processes until then, we call it as the subcortical processes, and the processes in the auditory cortex, we call it as the cortical processes. So the subcortical processes are well studied, and it has been well documented and well modeled. So there are models for the different processes up till that stage. So in this talk, we'll be mainly focusing on how we can model or derive inspiration from the processes in the auditory cortex. Just to go over the brief steps of modeling the subcortical processes, the incoming waveform is analyzed along a bank of asymmetric filters, which are uniformly placed on the logarithmic axis. So what this does is it analyzes the energy present along different frequencies, and we then to sharpen these filters, we apply a lateral inhibition. You can consider this as a derivative along frequency. So this effectively sharpens the bandwidth of the filters. And finally, there's a smoothing operation which mimics the processing in the midbrain, where there's a loss of phase locking. So we end up with something which is similar to a spectrogram. We call this auditory spectrogram. So here we are going to talk about what we can do to model the cortical processes. So we came up with a filter bank which looks like this. So what this does is it analyzes the spectrogram for various different patterns. So these patterns look like this. So what it's going to do is it's going to look for energy rises and energy falls and so on. And we are doing that at different scales or different what we call it as modulation. So for example, this one is very slow in time, whereas this one is extremely fast in time. So these are capturing the different modulations in time, and similarly you can see the same thing along frequency. So once we have this bank of filters, we can what this effectively does is maps this time frequency into a high dimensional space, where the different axes could be this spectral profile, the temporal profile, time frequency, and you can even think of adding different feature dimensions here like pitch and so on. So one quick motivation of why this could be a useful representation. So what we did here is we collected many examples of cello and flute notes, and we averaged the representation. So this is the average representation for these two instruments in that high dimensional space or the cortical space. And you can see that most of the energy for cello lies in a different space as compared to the flute. So this clearly shows that if you move to this high dimension space, the two auditory objects which are overlapping in time are now really well separated in this space. So you can think of doing multiple things in this domain. So now I'll talk about how we are going to analyze the effectiveness of such a representation for different tasks. So the first task I'm considering here is the speech recognition task. Then I'll later talk about timbre recognition and so on.
So this representation, is this the same as the kind of Shama, Nima, Eskarani? I mean, like other people have been doing.
Yeah, it's similar to that. Yeah.
So you're basically working with that representation.
No, when we move from the cortical stage here is different from their model. So they have filters which are modeled on the actual neural responses, whereas mine is just a generic 2D Gabor filter bank. So it's similar. You can.
If you go a slide back, one more slide back. So this is quite typical. This is
the
Shamaslam.
Yeah, this is the Shamala.
Okay, and the next slide. So this is already something which kind of starts to diverge.
Yeah.
So how many features you can extract with those filters? How many are those filters?
So if you want think about this, we have around 200 of these filters, or 220 filters, and so what that does is, if we have multiple frequency channels, so it's going to represent it into a really high dimensional space because of that.
So pretty much you applied that filter on the spectrogram, and the output is, do we have something like this in that particular time frequency space?
Yes, so the output activity is going to show how much of a match we have for this kind of pattern in this spectrogram.
So we have 4 dimensions: time frequency and spectral and temporal profile.
Yeah.
Thanks.
So I'm still a little confused. I thought, for example, like they had this, one of the sort of successful.
So the differences in the
sorry, just go ahead.
So the differences in the characterization of these filters.
Okay.
So they use the filters which are actually modeling the neural like the neural responses, whereas mine is a generic.
Oh, so the shape.
Filter shapes, yeah.
Whether it's a
specific
model or just a Gabor filter.
Yeah.
But the motivation is the same.
Yeah, the motivation is still the same.
Okay. So I mean, in both cases, you end up with a representation like that.
Yeah.
Like 3D or.
Yeah.
For every. Okay.
So one note on this, when we're doing some kind of statistical analysis, a high dimensional representation has its own pros and cons. So what happens is machine learning or the backend stage cannot handle effectively high dimensional space. So it's around we have like 28,000 features at the end. So it cannot effectively handle this many features. So what we will have to do something depending on what's the task. So for speech, we notice that preserving this temporal information is extremely crucial, because if you want to recognize speech, you need to have the sequence of phones which are on the order of like 100 milliseconds. So this temporal characteristics is extremely crucial. So, and also the machine learning setup cannot handle high number of feature dimensions again. So what we do is, instead of modeling these neurons as a filter bank, we are going to model whole group of neurons. So by that, what I mean is, so just to give you a motivation, look at the spectrogram here, and what we do is we take a cross section of the spectrogram along time, and this is 1 second in duration. So you can see that there are 5 distinct peaks in the overall temporal profile. And similarly, in the spectral profile, you can count that there are like 4 peaks in the spectral profile. So if you take a 2-dimensional FFT of this spectrogram, what's going to happen is all the energy here is going to be localized because of this characteristic. So the main peak is around 5 Hertz, and in the spectral domain, it's below what we call as 1 cycle per octave. So this motivates that instead of, in this 2D FFT domain, instead of having multiple filters, what we can do is we can capture the region of speech, which is capture the region which contains only speech information. So what we did then was so to try which regions are most effective to do speech recognition, we tried 3 different filters. So we call the suboptimal 1 speech-centric and suboptimal 2. The actual filter shapes are given here on the temporal axis and the frequency axis. The dotted line is the actual shape of the filter. So what we are testing here is how much of this region we need to capture. So the results of these 3 filters is going to tell us how much we need to capture. So the test that I'll give you the details of the experiments. The spectrogram is around 128 dimensional. So if we do that modulation filtering, we still have a 128 dimensional representation. So then we append the delta features on that. So we end up with a 500 dimensional feature representation. And we test it on a phoneme recognition experiment on Timbre. And during testing, we are going, this is a mismatch condition, so we are training on clean, and we are testing on additive noise cases. So only the test set is corrupted with additive noise from NoiseX database. And for the back end, we have a hybrid HMM MLP setup. And the MLPs here are stacked, so we have two MLPs which are stacked. So and we have around 6 layers of neurons. So the results of that experiment, what you can see here, if you are just considering the clean case, obviously keeping the entire information is the best possible case. So if you are trying to reduce the information, you're going to lose some of the performance. But when you go to the noisy case, when you're adding different kinds of additive noise, so what happens is if you keep the whole space, the noise, all the noise is included, and you're going to take a huge hit in performance. But when you're when you're reducing the space and trying to concentrate only on the speech, we found that the speech-centric filters is the best. And one thing to note here, that suboptimal 1 is always less than suboptimal 2. So suboptimal 1, if you go back, is removing some of the speech regions over here, whereas suboptimal 2 is including some of the noise. So it turns out that removing some of the speech regions is more hurtful than including a little bit of noise. And then we...
Sorry, what did you said we had a stacked MLP.
Yeah, so we have, so what we do is the first MLP, we just have, so we take these 512 features and we map it to the phonemes. And the second one, we include context on that. So we have, I think, 10 frame context on that. So we are trying to include some
10 frames of posterior estimates.
Yeah.
And then come with,
Yeah.
then predict.
Then again predict the phoneme.
Can you return a couple of slides back when you showed the one more? Okay, here. So technically what you do, you get the entire utterance, the spectrogram, convert it into that modulation domain,
Yeah.
apply the filter, convert it back to spectrogram, and then basically feed the regular speech front end.
Yeah.
So can we say that this is a kind of a speech enhancement algorithm? Because from the spectrogram I can convert back to time domain and see kind of the noise missing.
Yeah, so it's a little bit tricky to go back from this is the auditory spectrogram, so we try to go back from there, and we try to actually listen to the sound, and it wasn't that much obvious that it's doing speech enhancement at the signal level.
But you did convert to Timbre and listen it.
Yeah.
So how it sounds? A little bit noisier than you expect to? Or
if you compare just the noisy reconstruction versus this one, we couldn't find that much obvious difference in the quality of the sound.
Interesting.
Yeah.
But there's no.
So like the steps to going back from this auditory spectrogram to this signal is a little bit of an estimation involved in that. It's not straightforward. So
because you use the standard speech front end, which is 5 milliseconds a frame and 10 millisecond step, right?
Yeah.
Okay. So, good. Sorry, one question. So there's nothing about this approach that requires any of that other representation. I guess that's my. So, I thought it seems like you take a spectrogram, do a 2D FFT of the spectrogram, do the filter.
We are considering only those modulations which are important for speech. So effectively what the original representation I was talking about is going to sample points in this space. And if we do that, then we are going to increase the feature dimensionality. So another way of thinking of the same thing is where you want to sample it and just extract that region.
So you're just, based on this, deciding which of those other things to pick?
No, we don't pick those features because the speech backend cannot handle like that much dimensionality. So what we do is instead of picking those points in this region, we pick the relevant region in the space. So we are not, the motivation is kind of the same, but we are not using that feature set.
Oh, okay.
So we then compare this with two standard approaches where we apply MVA on MFCCs and PLPs, and we are able to outperform both of these standard techniques on clean and all the considered noise cases. And just a note that in our technique we used the feature dimensions don't vary that much between the baseline and our approach.
So what is the baseline? What is MVA?
So MVA is mean variance ARMA technique. So what that does is MVA it combines substral mean subtraction, variance normalization, and some kind of ARMA filtering, which is similar to Rasta filtering.
You never compare with other enhancement techniques, like speech enhancement.
No, we compared it with some other features, which I'll talk about a little bit later, but I don't know what you have in mind.
Like spectral subtraction,
or linear filtering,
or like advanced front end.
Yeah, we compared it with advanced front end.
So and is one other difference, am I correct, if you go back, that your system has an input that has 9 frames of context as a feature, and the other system is just a 1.
Yeah.
How common is triple delta?
It's common. I mean, people usually do that and then reduce the dimensionality.
So on average, we see that speech-centric filtering outperforms this MVA technique by 12 to 14%. There's some evidence in the studies which look at the auditory processing, and there's some evidence that the processing actually happens in multiple streams. So the brain actually divides the incoming information into slow dynamics or slow temporal dynamics versus fast dynamics, and they process it, and it's later the evidence is combined at a higher level. So we wanted to do a similar divide and conquer strategy so that the machine learning stage can take a maximum advantage of each of these streams. So how we divide the space into different streams is based on these 3 principles. The first one is information encoding, where each stream has to have enough information. Second one is complementary information technique principle, where each stream should be unique compared to the other streams. And finally, noise robustness, where each stream should contain only the high SNR speech regions. So the way we do that is, again, look, this is the same modulation domain, and we divide that into these three streams. And so if you see the information encoding principle, according to that, we divided these streams which have at least 60% of the energy in this entire region. Then each stream has some unique part compared to the other streams. And finally, they're still localized on the speech region. So this has to, we hope that this gives noise robustness. So an example of how these three stream of the three filtered spectrograms would look is like this. So the first one is including only the low temporal and spectral modulation, so it's smooth in time and frequency. The second one is allowing for higher frequency modulations. So you can see it's a little bit more faster along frequency. And the third one allows for a little bit faster along time, so it's not as smooth as the first one. Again, the back end is almost similar to the first experiment. So instead of having one, so we have the same setup for each of the three streams, and we combine the evidence using the product rule. So we're combining the posteriors at the very end. And we test this not only on additive noise, but in this case we tested it on channel noise and artificial reverberated test conditions. In this case, we compared it with one other baseline, which is the ETSI Advanced Front-End Baseline. So on this one, they do voice activity detection, and they're doing, they estimate the noise, and they're doing some sort of noise cancellation as well in ETSI. So ETSI, if you look, it's built for additive noise, so it does really well on additive, but it does not do as well on the other kinds of noises. But when we compare our approach, we see that we are doing, we beat all these systems not only on clean but all the other noise conditions as well by a significant margin. So as I said, ETSI has these additional advantages of voice activity detection. We don't have anything like that, and we are still able to beat those by around 4 to 19% depending on the noise conditions. And if you analyze the different streams, we saw that stream 1 alone can beat the baseline on most of the noise conditions, and stream 2 and 3 then add on to this to give us the best advantage. So now I'll talk about how we adapted this auditory object representation for timbre recognition. Typically, when people look at timbre, they're trying to identify what are the dimensions of timbre. So when I say timbre, it's defined as anything which identifies the instrument, and it's not volume and pitch. So anything apart from volume and pitch which you can use to identify the instrument. So a lot of studies, they look at, so they collect human studies where the human subjects rate how different they perceive two instruments, and based on this, let's say perceptual distance of the instruments, they map it into a 2-dimensional or a 3-dimensional space. Then they try to find features which correlate with the dimensions of the space. So they are going about and finding the dimensions of timbre in that approach. Here we take a more the reverse approach, where we define the dimensions of timbre and we see how well it matches with the perceived distances. But first we'll do a quick analysis of this representation on the classification task. So here we keep the full representation. So we are keeping this full high dimensional space because to identify the timbre of an instrument, it's really key to have all the spectral and temporal variations, and we can afford to lose the temporal fine structure. So we keep the whole space, and we test this on RCW musical instrument database. So this has 11 instruments, and it has like close to 2,000 notes per instrument. For each instrument, they have 3 different manufacturers, and they have multiple playing styles, and they play all the possible pitch values on that instrument. So we are really testing if our system can generalize to this. So what we do is we take this high dimensional representation, and we try to reduce the dimensions to a manageable amount using tensor SVD. And for the back end, we are going to use SVM classifier with RBF kernels, and I'll talk about the last point later. So when we do this, we are going to compare this sort of representation with 2 other representations. So the spectral features here is just the auditory spectrogram, and we use that as the. We also tested it on features like MFCC. So they all give something in the range of like 79%. So this second feature set that we compared is actual neuron transfer functions that were recorded in University of Maryland. So we borrowed that, and this has around, I think, 1,200 neuron transfer functions. So we just applied those to the auditory spectrogram, and we used the activity of that to classify the timbre, and we saw that that's able to do quite well as compared to the spectrogram. But the problem with that is it doesn't have the full range of so it's just 1,000 neurons, but our brain has millions of neurons, so it's not able to accurately capture the entire range of possible neurons. So if we use a model of this, our model, we see that we are able to get really good representation for these instruments. So this shows that these instruments are really well separated in this region. So I was talking about how these instruments are separated in this space. So what we wanted to do is to see if this model captures the perceptual distance that human subjects have stated. So we went ahead and had human subjects rate how different they perceive these instruments from this RCW database, and we have some sort of matrix which tells how different these instruments are. And we then take the distances in our model, and we just do a correlation with these distances, and we see that when we do it with the baseline features, they're not correlating that well with the human distances. But with our model, we see that the correlation is also pretty high. So this shows that this representation is not only able to separate the instruments, but it's also able to keep the distances between the instruments as we perceive it. So then this was just based on isolated tones of instruments. So we thought how we can use this in a more generalized situation. So you might have, if you go and buy a musical recording, you might have something like this. So this is a artist playing an instrument, and whereas our model was trained on something like this, which is a clean tone, which has the full rise and the decay of the tone. So it's allowed to decay completely, and we capture all the dynamics there. So if you test our system on this, just using uniform windows, so you don't care about what's actually there. So you see that the classification accuracy drops drastically from 98 to 70. So this shows that so these recordings were we actually collected from commercially available CDs, so there could have been some differences in the recording equipment and so on. But as I was saying, since these notes are isolated notes, we think we can do better if we can extract the notes from these from this continuous recording. So we tried existing techniques for onset detection, which tell you the boundaries between two notes, but they were not able to generalize well to this database because we have recordings from various different studios and different CDs, so it was not able to generalize, because we think that it's because most of the systems work on the signal level representation. So what we did was we came up with this idea. So here what we are going to do is, if you look at one particular note, you can see that the harmonics are placed along different points in the frequency axis. So if we come up with a template which mimics the placing of these harmonics along the frequency axis, and if we see how well this matches, how well the pitch template for each pitch matches the spectrogram, we can get some sort of pitch estimate, and we mark those regions where the pitch estimate is changing as the possible times for onset detection, and also the degree to which it matches is we call it as harmonicity, and we typically see that at the boundary of two notes the harmonicity is low because there are overlapping harmonics. So we also match the we mark those candidates where the harmonicity is low as possible onset boundaries. So we then combine the evidence from both of these streams to get reliable estimates for onset for the pitch bound for the note boundaries. Then what we do is we then extract, we segment this continuous recording along these boundaries. And then if we do note extraction, we do the classification on these extracted notes, we see that we get a performance improvement of close to 9%. But to take care of the differences in recordings and other changes in the statistical distribution, we can also adapt the backend. So what we did was we have a few examples of these. We take a few examples of these extracted notes, and we adapt the SVM boundaries to this new distribution. And if we do that, we see that we can further improve the performance by around 6%. So this obviously has the advantage of having a few examples that it has seen, whereas the note extraction does not have that advantage. So a few observations, we were able to not only represent a musical timbre in the space, but we are also able to capture the distances between the instruments well. When we did a study of the marginal representations, like do we need to keep the whole space or can we marginalize it along different dimensions, we saw that the whole space is indeed required, and we also saw how it can be modified to be robust to out-of-domain conditions. So now I would like to talk about the concept of attention in this space. So when I say attention, there are usually two kinds of things that are thought about. So one is the bottom-up attention, where you are not doing anything voluntarily, but let's say there's a loud bang somewhere in the background, you immediately divert your attention to that. So that is the bottom-up attention, and we are going to talk about something called as top-down attention, where I give you the task to pay attention to some particular sound or some particular object, and without this task you won't be able to recognize it, but once you're given the task, you'll be able to recognize it. So that's the top-down attention that we are going to talk about. So for example, in the visual domain, if this is the visual scene that there's there, and I ask you to pay attention to this painting on the wall, so you'll do something like a field of view sort of thing where you're able to restrict your faculties only to that particular object, and you're also able to change or move this field of view to a different object, like if I ask you to pay attention to the flowers. So how does this work in the auditory domain? So for example, from this waveform, you won't be able to tell that there are multiple objects. So I'll just play this sound to you.
0, 0, 5, 7, 9, 2, 7, 4, 0, 3.
So as you notice, there are multiple speakers in this recording. And if I now ask you to repeat what the male speaker said, I'm pretty sure nobody is able to do that. But now I give you the task to pay attention to only to the male speaker, and let's see if we can do that again.
0, 0, 5, 7, 9, 2, 7, 4, 0, 3.
So you are able to pay attention to the male, and you are able to say it's 3, 8, 5, 5, and so on. So this clearly shows that there's something that's happening where you can focus your view from one object to the other, even in the auditory domain, similar to what was happening in the visual domain. So we wanted to implement this in our model. So some studies on what actually happens in the brain, they show that this is a transfer function of one particular neuron in a ferret, and the ferret is now asked to pay attention to some particular event. And when it's doing that task, the transfer function changes. So this clearly shows that the representation in a auditory cortex is not static. So the representation is changing, whereas our representation was sort of a static representation. So we want to implement some kind of adaptive technique to take care of this. So the motivation is, like we saw, two different objects occupy two different spaces in this space. So let's say we had animals and music, and they're occupying different regions. So if we had to pay attention to music, if you had some prior knowledge of music that it's there in that location, you can focus or highlight that region in the space because they are well separated. So that's the hypothesis. And the way we implement that is we collect we collect some prior data for that instrument or that object, and we have the mean representation of all the activations for all the filters. And what we then do is, if the task is to pay attention to animals, we use that activation pattern as a boosting, or you can call it the gain adaptation for these filters. So we boost those filters which are most active during the target class, and we suppress the other filters which are not so active. And there's also evidence that the higher stages of processing also undergo changes during top-down attention. So we can think of that as something like our statistical model is adapting to this new task. So we do a map adaptation in this case. Given a few examples, we map adapt the target distribution to the new conditions. So the way we test this is we have a BBC sound effects database. So this is quite a big database it has 12 classes and 46 hours of data. And during testing, what we do is we artificially mix the target class with other target classes, so there are multiple sources occurring at the same time, and we tell our model to pay attention to only the target, and we see how well it does at this recognition. So in this case, the feature dimension, we were able to reduce it to 113 as compared to the music where we had to keep more. The backend, as I said, is a GMM classifier, and we use map adaptation to adapt the models. So when so the performance here is measured in D prime. So this takes care of not only the not only the true positive but also the false. So it takes care of the false alarms and the true positives. So we are not just looking at how many times you identify it, but how many times you wrongly identified it as well. This is a more robust measure. We compared it with this MFCC baseline, where we are averaging the statistics for the entire duration of that recording. We take the first, second, and third moments of the MFCC features and use that as the feature vector. We also recently compared with more standard acoustic features that are there in the literature, and we found that they're all comparable to this range of performance. And in our model, without any attention, so no boosting, no adaptation of the GMMs, we see that we are already getting a big gain in performance. So this shows that probably our model already has these objects well separated, so we are able to do that. But when we apply boosting, that is when we apply the gain and the filters, we see that the performance improves, but not that much. So this shows that probably there's some change in the statistics that the GMM backend is not able to handle it.
So, sorry, boosting is not the machine learning version of boosting. I mean, it's not boosting like the machine learning.
No,
it's just adding.
It's just the gain boosting filters. And when we just do the adaptation and no boosting, we see a higher jump in performance. So this shows that this may be because that for doing the GMM adaptation, you need some sample examples of the test conditions. So that's why it might be doing better. And finally, when we combine both of these techniques, we get the best performance. So this shows that when we boost the filters, we need to actually adapt the GMMs as well. So we are getting the best performance when we do both of these techniques.
So sorry, so when you say adaptation, do you mean unsupervised adaptation or supervised?
It's supervised.
Supervised, you already have some samples.
Some samples.
Yeah, I'm sorry. So how does boosting work, like, exactly, or more specifically?
So let's say we had those we had like many filters. So we collect for the target class, so given a target class, we collect from the training data the average representations or the mean activity for these filters, and we normalize it to be in the range of, let's say, 1 to 0.5, or we can control this parameter. So these activations are now in some range, and we use that as the gain parameter for the filters, and we want to pay attention. So let's say filter 1 was active for speech, and filter 2 was not active for speech, but it was active for machines. So when we apply this and we pay attention, when we are asking to pay attention to speech, so filter 1 will still be on, or it will still be active, versus filter 2 will.
So you're like normalizing the responses by the average response of that class.
Yeah. So we saw that this cortical representation is able to, we got around 45% relative improvement on the baseline, and this representation was able to also facilitate an attentional mechanism where we could selectively attend to the targets, and we showed that these attentional mechanisms provide 81% relative gain. That's a huge improvement. And more recently, we were also able to not only change the gain of the filters, but we were also able to adapt the shape of the filters depending on the target. And we showed that this was more useful for adverse conditions when the target to masker ratio is really low.
Which filter shape? The set of the 2D Gabor filters?
Yeah, these filters.
So you are thinking about adding a different set of those base filters with different shape?
So the base, let's say we have a model trained like this, and given a target, we are changing the orientation of these filters a little bit, and in a manner so that it's most active during that target class. So if you change
the finding a more suitable alphabet.
Yeah.
So when you design those filters, do you actually use a data-driven approach, or you actually manually design this?
So it's just you can think of it like a 2D wavelet transform. So we have the base functions and we just so in conclusion, we presented a multidimensional, possibly over complete space, which can represent auditory, which was motivated from the auditory system processing. And this space we had sensitivity to frequency, temporal profile, spectral profile, and we showed how this space can be a basis for many different sound technologies like speech recognition, timbre classification, and scene classification, and also how the space facilitates the creation of attentional mechanisms, and how we think that such a mechanism can be a basis for tasks like event detection or keyword spotting and so on. These are some of the publications which resulted from this work. So you have any questions?
Questions, dear colleagues?
I do a clarification.
Yeah.
You can go to any of your speech recognition slides. So I'm just trying to compare the different systems. So the MFCC or PLP systems were GMM systems.
For the speech?
Yeah. So like you got to go to the speech recognition, the initial Timbre. I don't know who had the. Yeah. So those two first columns were GMM systems?
No, there's still the back end is still the same as the hybrid HMM MLP.
Okay, so it's one window of MFTCs into it.
Yeah.
HMM, neural net, MLP, predicting posteriors, and then scored with it. And that one is just many windows, the two-stage thing.
No, the back end is the same for MFCCs and our system.
Right, but the speech input to the MLP is the context window of, it's the two-tier, you have this two-stage hierarchy.
So we still have that for MFCCs as well. So it's exactly the same. Only the input features are changing.
And the other question is, it looked like on all the other tasks you used this tensor SVD, but you didn't use it here?
No, because here the feature dimensions were manageable. It's still in the 500. The feature dimension was 500, so we have a MLP with input layer of 500.
Well, that's because you did this manual extraction.
Yeah.
So have you tried just taking the big thing in and tensor SVD and sticking it in?
That was the very first naive approach, and that didn't work out.
Okay. Any idea why it worked there or not?
Yeah, so I think in that case, so what happens is I think the features are redundant, I think, in some way, and we are not able to capture this. So we lose some sort of temporal structure. So let's say we have filters which are quite broad, and we are trying to find the correlation, the convolution and time. So we are losing the time, the output will lose the temporal structure. So we are getting some smooth response. So we are not able to predict the phone sequence from that. Yes?
So in one of your early slides, the motivation slide, you showed that we can listen to an orchestra or three musicians playing and recognize the instruments and things.
Yeah.
Can a computer do that? In other words, can we do this automatically? Are there programs out there, has there been research published, that can successfully take an orchestra or multiple instruments and separate the sound into each instrument?
There are some studies which do, I'm not aware of studies which do exactly identifying the instruments, but they do some sort of on this multi-source environment, they do different processing, like identifying the genre of the music, or identifying like different characteristics of the music, but maybe not finding out which instruments are playing.
But the work you showed on attention, right?
Yeah.
I mean, couldn't that just be applied to the problem if you can separate the male from the female speaker, or the various sources? Couldn't you just apply that system to that problem?
I think the way we formulated is given a target. So given you have to pay attention to piano, we were able to tell to a better extent if piano is present or not.
Right.
So we would have to then apply this for all the sets of instruments, and then we could in that case we can tell which instruments are present. So we would have to run the system on different targets and see which of these targets are present.
Okay. Well, I think that would be a very interesting application to see how far you can get.
And once we started to talk about other applications of pretty much a new feature set you can extract from the audio signal, how applicable is this for other tasks? Let's say getting a non-verbal cues from human speech, emotion, speaker identification, even gender, age.
Yeah.
Do we see an application for such, this new feature set for such application?
I think definitely I can see some advantages of using such a representation, because we are not after capturing. So in timbre we were after capturing anything that is apart from pitch and volume. So we are trying to capture all the characteristics of that instrument. So I think for an example, if in the musical instruments, I tried just doing a broad instrument recognition. So we can recognize if the instrument is a string instrument or a wind instrument or a percussion instrument. So by using similar features, so that shows that it's not only capturing one characteristic, but we are able to generalize it to capture different characteristics of the sound. So the way you're saying, like if you want to capture
let me rephrase this question to you a little bit. So my understanding is you can separate or detect the presence of, okay, there's this cello, or there's a flute, or there's whatever. And you had some recognition rate of 90-some%.
Yeah.
If I gave you 3 cellos and asked you, which of these 3 was playing when, what do you think your recognition rate would be on which one of the 3 cellos?
So I think if you are given 3 different cellos which have slightly different characteristics, I think we should be able to capture the minute differences between the instruments as well.
So you think from the timbre you could get, again, this like 95% recognition of which one it is?
If we change if you have different manufacturers so you're talking about different kinds of instruments, right? Different for in a cello you might have different. So
let's assume I don't know much about cellos, but let's say a really expensive one and
Can you recognize a Stradivarius violin from some normal production?
I think another good example for that would be, given a cello, you can play it in different styles. So you can have the vibrato style, or so that the musicians use that to kind of to emote. The same musician, same instrument, but he's trying to express his emotion by different style of. Yeah.
So you really think you get that same kind of recognition rate, separating the 3 cellos as you do from separating a cello from a flute?
I think it may not be in the 99% range, but I think given if there's unique characteristics, I think we can do a really good job at capturing these characteristics.
That would be impressive. So I guess the obvious other one is now you have 3 similar, 3 30-year-old male speaking, and you think you recognize which one is which?
Yeah, I think we can. It's like the timbre of human speech. So
Yeah, well, that might be optimistic because the timbre between a male and a female is quite a bit different than between myself and Michael, right? So it's all a question of degree.
So,
Yeah.
I mean, it's just, I'm just asking because,
So we actually did speaker verification experiments using features similar to this,
Okay,
and we were able to beat most of the standard approaches.
but did you do it under the cocktail party condition where there were two people speaking?
No.
And you said out of the 10 people in the database, tell me the two people who were speaking on top
So
of
we
each
had
other.
background we had background noises with
right?
babble
So
noise
they
and
get
so
the
on.
adaptation. If the noise is very different, you know, if it's sort of low rumble or music or something,
Yeah.
I mean, it's a very attractive approach, both the idea of filtering for the signal and adapting. But, you know, I think there's the fascinating stuff is how far you can push it. The idea is elegant, but I don't have any sense that you really know how widely it applies at the moment under more challenging conditions.
It's valuable actually even if you can distinguish and sort out speech, non-speech, because
Sure.
in most of the cases, at least today, we have one speaker talking to the dialogue system for speech recognition.
Right.
Or even if you can detect, okay, this uterus belongs to speaker 1 to 8 or none of those. Those are the typical scenarios which, at least for are in kind of a process of getting applicable in real systems. More questions?
Okay.
Let's give a big round of applause.
Thank you.